Hi, this is S. Lakshmanachari, working as Assistant Professor in Department of Cybersecurity, Institute of Aeronautical Engineering, Hyderabad. In this lecture, we are going to discuss a relatively simple instruction set architecture. So, the ISA, so instruction set architecture. So, instruction set architecture, it is abbreviated as ISA. So the instruction set architecture, it defines how the CPU is controlled by the software, and the instruction set architecture, it refers or it includes the various data types, instructions, addressing modes, and exception handling, interrupt handling, external I/O. So these are all the different the instruction set architecture it consists. So it describes this lecture. It describes the instruction set architecture of a relatively a simple microprocessor or the central processing unit. So this CPU was designed as an instructional aid and draws its features from several real microprocessors. The microprocessor is limited to run away anything as complex as the personal computer. However, it has about the right level of complexity to control a micro oven or the other consumer appliances. So here, mainly in this lecture, we are going to review the memory model, and registers, and finally we will see the instruction set that is associated with the instruction set architecture. So let's start with the memory model. So every processor, the memory is an important resource, because the memory using the memory we can store some programs and the data which are related to the program that can be run by the processor. So this microprocessor can access 64 kilobytes of memory. So this microprocessor, it can access up to 64 kilobytes of memory, because it is having a 16-bit address bus. So the memory size can be calculated using the formula 2 power n. So that means 2 power 16, that is equal to 64 kilobytes. So that means the processor can access up to 64 kilobytes of memory, and with each byte having 8 bits. So each byte having 8 bits. So or 64k by 8 of memory. So this it represents 64k. So that means 64 kilobytes bytes memory locations are there, and each memory location size is 8 bits. That means in every memory location we can store 8 bits of information. So this is a 64 kilobytes is the maximum memory it can access by the processor. So it doesn't mean that every computer constructed using this particular processor, simple CPU, must have full 64 kilobytes of memory. So it doesn't mean. So that means if you design any project with this particular microprocessor, it doesn't require to access the entire 64 kilobytes of the memory. So we can use less than that also. We can use, suppose if we require only 30 kilobytes, then we can use the 30 kilobytes only. Okay. So the system based on this microprocessor can have less memory if it doesn't need the maximum 64 kilobytes of memory. Suppose if we doesn't require the entire 64 kilobytes, so in that case we can use whatever the memory size we want. Suppose if we want 30 kilobytes of memory, then we can use that only. Okay. So there is no rule that we can use the entire size of the memory. So in this processor, including the data from and outputting the data to the external device, such as the oven's keypad and the digital display. So these are the two these are the input and output devices which are related to the microwave oven. So for the microwave oven, we are giving the inputs using a keypad. So using the keypad, we are giving some inputs. Then it will process some operation. Then the results will be given to the user by using a digital display. Okay, so this reading from the keypad and writing to the digital display, it seems to be treated as the memory access. And here there are two types of input-output interactions that you can design a CPU to perform. So mainly we can perform two types of operations with the I/O devices. The first one is the isolated I/O, and the second one is the memory mapped I/O. So isolated I/O. So isolated I/O, the input and output devices are treated as being separate from memory. So that means isolated I/O. That means the name it specifies the meaning. That means the memory mapping, the address for the memory and the addresses for the I/O device are separate, are not using the same address. They are separate. So that's why it is called isolated I/O. So here you can see the figure isolated I/O. Isolated I/O. So here we are using the memory device and the I/O device. So this memory device and I/O device, they are using a separate addresses. So a separate addresses are there for memory as well as the I/O. Okay, so that's why it is called isolated I/O. And also in isolated I/O, the memory and I/O devices are using a common address and data buses, but it is using a separate control signals. It is using a separate control signals for both the memory and the I/O devices. And coming to the memory mapped I/O. So the memory mapped I/O, on the other hand, treats I/O device as the memory locations. The CPU access these I/O devices using the same instructions that it uses as to access the memory. So that means in memory mapped I/O, the same instructions can be used. The same instructions can be used in order to access both the memory as well as the I/O devices. Okay. So here that means the address space for both the memory as well as I/O devices is same. Okay. So that means if you have some area, some portion of the memory, then this entire memory space we can use for both the memory as well as I/O device. Okay. So that is a memory mapped. Okay. So coming to the comparison between the isolated I/O and the memory mapped I/O. So in isolated I/O, different address spaces are used for computer, memory, and I/O devices. So already we have seen. So we are using a separate address spaces for both the memory as well as the I/O devices. So that's why it is called isolated I/O. And I/O devices have a dedicated address space. Okay. And memory mapped I/O. So same address space used for memory and the I/O devices. So that means so we have a memory. So this entire memory we can use it for both the memory and I/O devices. But whereas in isolated I/O we have a separate memories for the memory and the I/O devices. Okay. Next one, a separate control unit and control instructions are used in case of I/O devices. Okay. So in isolated I/O, we are using a different control units and different control signals in order to access the memory as well as I/O signals. But whereas in memory mapped I/O, the control units and instructions are same for accessing memory and I/O devices. Okay. And the third one is more complex and costlier than memory mapped I/O as more buses are required. Here in isolated I/O we are using a different buses for both the memory as well as IO device. So in this isolated IO, we require more number of buses. So that's why the complexity of the system will be increases. Similarly, as the number of buses increases, the cost also increases. But in the memory mapped IO, it is very easier to build and cheap, because here in the memory mapped IO, the same bus lines we are using in order to access the memory as well as IO devices. So here the less number of buses we are using. So that's why the cost and complexity also reduces. And the entire address space can be used by memory as IO devices. As IO devices have separate address space. So here in isolated IO, we have a separate address space for both memory as well as IO. Some part of address space of the computer's memory is consumed by IO devices as address space is shared. So, see, if you have a memory that entire, so some portion it is allocated for the IO device. Okay, so that means entire the IO address space and the memory address space both will be overlapped in the memory mapped IO. So that's why more address space is there for the memory mapped IO. And computer memory and IO devices use the different control signals for read or write. So already we have seen in previous. So we have a separate control signals in order to for read and write for the memory and IO. Suppose if you are reading and writing from the memory, then we are using IOM, IOW. That means if you are reading and writing to the memory, so memory read, MEMR, memory read, memory write, MEMW, memory write. Similarly, when we are writing and reading from the IO devices, so IOW, that means IO writing, and IOR, IO read. So like that, we have a separate control signals for in order to read and write the data from the memory as well as IO devices. But in the memory mapped IO, we are using the same set of instructions, same set of control signals in order to read and write from the memory and IO devices. And the last difference is the separate control bus is used for computer memory and IO devices. So same address and data buses are used. And address, data and control buses are same for memory and IO devices. So in the isolated IO, we are using a separate buses in order to access the memory and IO devices. But in the memory mapped IO, we are using a common bus for accessing. And coming to the second thing, that is registers. So registers. So registers. So basically, the processor mainly it is having 3 registers in ISA of this processor, that are accumulator. First one is a accumulator. Second one a register R, and third one is a 1-bit 0 flag. So these are the mainly it consists in the ISA of the processor. So accumulator. So accumulator is it is one of the important register in general purpose registers. It is a general purpose register, and the size of the register is it is a 8-bit. It is a 8-bit. So that means this particular register it can store 8 bits of information. As in many microprocessor, the accumulator of the CPU receives the result of any arithmetic or logical operation. So whenever you perform the arithmetic or logical operation, the result automatically it will be stored in the accumulator. Okay, so that is a accumulator. So that means especially the accumulator can act as a default register to store the results when you perform any arithmetic or logical operation. It also provides one of the operand for arithmetic and logic operations that use 2 operands. Suppose if you wish to perform any arithmetic or logical operation, if you want to perform any operation, we should require 2 operands, 2 values we require. So one value will be stored in the accumulator and another value will be stored in the some other register. So the accumulator can be used to store the one of the operand in any arithmetic or logic operations. And in addition to that, the accumulator can also be used for the data is loaded from memory. Whenever the data is loaded from the memory, then first the data is copying from the memory into the accumulator. Similarly, when we are storing any data into the memory, then the data from the accumulator is taken and then it will be placed in the memory. So when we are reading or writing the data in reading and writing data from onto the memory, we are using this accumulator. And coming to the second register, that is a register R. So this R is it is also an 8-bit general purpose register. So already we know the register can be used to store some data, 8 bits of data. So the register can store the number of bits that depends upon the size of the register. If it is 8-bit, it can store 8 bits of information, and if it is 16-bit, it can store 16 bits of information. It supplies the second operand of all two operand arithmetic and logic instruction. And the third one is a 1-bit zero flag. 1-bit zero flag. So there are no instructions that explicitly set Z to 0 or 1. So in this process, we are not having any instructions that explicitly making the flags to be set or reset. So the flags will be set or reset that based on the operation performed. So whenever we are performing some arithmetic or logical operation, so based on the result, that particular flags will be become set or reset. So this is a Z flag. So Z flag means zero flag. So when you perform any arithmetic operation, if the result is 0, if the result is 0, then the Z will be set to 1. Suppose if I have a 1010, this is one value, and another value is 0101. So if I perform AND operation between these two values, then I will get the output as a 0. So output is 0. So when the output is 0, then the Z flag will be set to 1. If the result is non-zero value, then the Z will be equal to 0. So in this way, the 0 flag will be set to 1 or 0. That depends upon the result of the operation. And coming to the third one, that is the instruction set. Instruction set. So mainly here it consists of 16 different instructions, and each having 8-bit instruction code. So total we have 16 instructions and each having 8-bit instruction code. So instruction means instruction is a command to the processor to perform a specific task. So this instruction, it consists of mainly two fields. It consists of two fields. The first field is the opcode, and the second one is the operand. So opcode. So this opcode, it specifies, it describes the type of the operation to be performed. And operand. So operand is nothing but the data on which we are performing this particular operation. So by having these two enter this the opcode and operand together, we can call an instruction. So instruction, it is a command to perform a specific task. Example, add a comma b. So in this, add is an opcode. Add is an opcode. That means the operation we are performing is addition. That is a opcode. And this addition we are performing on the data which is stored in the registers A and B. So these are called operands. These are called operands, and this is a opcode. Okay, so this is an instruction. So total we have 16 instructions. These are the, so this is a NOP, means no operation, no operation. So the instruction mnemonic is a NOP, that means no operation, and its opcode is instruction opcode, or we can also call the instruction code. So 00000000. So this is a instruction code for NOP. NOP means no operation, nothing it will do, the processor. Next, load accumulator, LDAC, load accumulator. So that means the accumulator is loaded with the data from the memory, and its corresponding instruction code is this one. And STAC, store accumulator. That means whatever the value is there in the accumulator, that will be stored in the memory, whose address is specified by the this data. And move AC. Move AC. That means whatever the value is there in AC, that we are moving to the register R. And each instruction, it is having that particular instruction code. Let's move on. Let's jump. Jump. So this jump is an it is a conditional. Jump is an unconditional branching instruction. So that means by executing this jump instruction, the program control will be transferred to a new address instead of going to the next address. Okay, so suppose if you specify jump 5000, so whenever this executed, this type of instruction is executed, the program control will be transferred to the address specified in the instruction. Okay, so here what is the address? 5000. So the program control will be transferred to this 5000 location instead of going to the next address. So here this is a symbol we have used to represent the address part. Jump 0, jump if 0. So jump, that means it is a conditional. So the jump will be takes place if the condition is satisfied. What condition we are checking here? Here we are checking the 0 flag. So if 0 flag is equal to 1, then only the jumping will be takes place. Otherwise, no. Next, JPNZ. That means jump if not 0. So that means the jump will takes place if the 0 flag is not set. 0 flag will be not set to 1. That means 0 flag will be equal to 0. Next, addition, add. So its operation is, it is add. We are performing a addition operation. We are performing addition. So add AC comma R. That means we are adding the contents of register R with the contents of the accumulator. And again, after performing that addition operation, the result will be stored in the accumulator, because already we have seen just before, the accumulator can be acts as a default register to store the result. And the next, subtraction. SUB means subtraction. Increment, INAC, increment accumulator. That means this particular instruction will increment the value which is stored in the accumulator by 1. Okay, suppose if the accumulator it contains a value 5, then after incrementing it will become 6. Similarly, clear accumulator. So clear accumulator, that means the register will be clear to the register. That means accumulator register, it will be clear to 0. That means the register will be loaded with all the zeros. And operation, or XOR not. So and or XOR not. So not means complement operation. So these are the different 16 instructions. And just before we have seen the different instructions. So out of that, the LDAC, STAC, jump, JMPZ, JPNZ. So these instructions are all require a 16-bit memory address represented here by the gamma. Okay, so that means all these instructions it require a 16-bit memory address because these instructions are associated with the memory. Whenever if they are reading the data from the memory or writing the data to the memory, it requires a 16-bit address so that they could perform that particular operation. Otherwise, it cannot. Because in memory, if you want to access any particular memory location, we can do it using only the address, some 5000 or something. Every memory location, it is identified with a unique address. Okay, suppose if you consider a example, jump 1234H. It is a one instruction, jump 1234, jump. So jump is a unconditional branching instruction. That means here we are not checking any condition. Whenever we write jump 1234, immediately when the program control comes to the 25th location, then in the 25th location it is stored, the instruction jump is stored. So this whenever this jump is executed, the program control will be transferred to the this 1234H location instead of going to the next address. What is the next address? Next address is a 26, but the program control is not transferring to the 26th memory location. Instead of going to the 26th memory location, it is transferred to a new address whose address is specified in the address part of the jump instruction. Okay, so this jump instruction is in order to store in the memory, it requires 3 bytes. It requires 3 bytes. So 3 bytes is for, in order to store 34, it requires 1 byte. In order to store 12, it requires another byte. And in order to store the opcode, it requires 1 more byte. So total, we require 3 bytes in order to store that instruction in the memory. So the instruction would be stored in memory as. So just before we have seen. So jump 1234 H. H represents hexadecimal because all the values will be stored in the memory as a hexadecimal values. Hexadecimal or binary. So 34. So 34 will be stored in the one memory location. 12 will be stored in the another memory location. Jump will be stored in the some other memory location. So total it requires 3 memory locations in order to store. So in which order that instruction will be stored? For that we have a instruction format for relatively simple CPU. See, so this is a byte 1. This is a byte 1. Okay. So byte 1 will be stored in the first. So here. After that, the higher, after that, this. So 1, 2, 3, 4 is a one value. So in that, it is a lower. It is a lower byte. Lower byte. And it is a upper or higher byte. So always the upper byte it will be stored in the upper address. So see here, the higher order 8 bits will be stored in the here, and the lower order 8 bits will be stored in here. So if you look into the memory addresses, the jump will be stored in the 25th jump. So what is the opcode for the jump? So 00000101. So this is the opcode for the jump. So that the particular 8 bits of information will be stored in the 25th location. Already we know in every memory location we can store only 8 bits of information. So that's why 1 byte will be stored in the 25th location. So next one, 1, 2, 3, 4. So 3, 4 will be stored in the lower. So out of the 26th and 27, 26th is the lower address. So that's why the lower byte it will be stored in the lower order. Lower byte will be stored in the lower byte will be stored in the lower address. Higher byte will be stored in the higher address. So in this way, all the instructions will be stored in the memory. And coming to the different types of the instruction sets. So basically we have two types of instruction sets are there. So one is a CISC and another one is a RISC. CISC means complex instruction set computer and RISC means reduced instruction set computer. So CISC architecture gives the more important to the hardware, whereas the RISC architecture it gives more important to the software. And in the CISC architecture, we have a more number of instructions. That means it is having a complex instructions, whereas in the reduced instruction set computer, we have a reduced instructions. That means we have a limited number of instructions. And it can access memory directly. It requires registers. So only through the registers only it can access the memory. So coding in CISC processor is simple because here the more the instruction set is very complex. That means more number of instructions are available so that the coding becomes simple. Whereas the RISC architecture it has limited number of instructions, so that it becomes quite difficult to write the program with a limited number of instructions. As it consists of complex instructions, it takes multiple cycles to execute. So in the CISC architecture, it requires more number of cycles in order to execute the instruction. Whereas in the CISC, it requires single instruction to execute the instruction. Complexity lies in microprogram and complexity it lies in the compiler. And why are instruction sets important? So the ISA it is a fundamental building block for the building fast, efficient computers that optimize memory and processing resources. So that's why this ISA instruction set architecture it consists of it consists on supporting the following capabilities that are data types. So ISA it includes the data types, instructions, processor registers, addressing modes, exception handling, interrupt handling, main memory hardware, input or output model. So these are all. So the ISA instruction set architecture it consists of all these following capabilities. And programmers and system engineers should rely on the ISA for guidance on how the program various activities. So the designer must familiar with all the instructions which are related to the instruction set architecture so that they can program various activities. And instruction set works with the other important parts of the computer such as the compiler, interpreter. So these are so the instruction set it also depends upon these others like compiler and the interpreter. So these compilers and interpreters, the compiler can convert the high level language into the machine understandable language because we are writing the program in a using the high level language or the assembly language. So this high level language or machine language cannot be understood by the processor or machine, so that they needs to be converted into the machine understandable language. So that's why we are using a compiler. So compiler will convert the high level language into the machine understandable language, and those components translate high level language program coding into the machine code that the processor can understand. Okay. So how are instruction set commands used? So the instruction set command it can be used for various purposes like for data handling and memory management. So data handling means we can setting a register to a specific value, or copying the data from one register to the another register, or copying the data from memory to the register or register to the memory. So all these types of operations are under the data handling and the memory management. And the second one is arithmetic and logic operations and activities. Okay. So in order to perform various arithmetic operations like addition, subtraction, multiplication, division, compare. So these are all the different arithmetic operations. Similarly, the logic operations and or XOR, not, complement. So these are all the logic operations. And control flow activities. Control flow activities. One example is the branching instruction. So that means the program control can be transferred from one address to a new address based on the requirement. So that all will comes to the category of control flow activities. So mainly the instruction set commands can be useful for the data handling and memory management, arithmetic and logic operations, and the program flow activities. So in this lecture, we have seen a relatively simple instruction set architecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.